All right, y'all. Way to stick with it. This is our last lesson. Minus if you need to watch the jump or R videos about multiple linear regression for this week. We're going to end on talking about the R squared diagnostic through seeing what the definition is, understanding what it's kind of doing, and then doing an interpretation with the fish catch example. So R squared is also known as multiple coefficient of determination. It is rarely called that, but if you're trying to Google it, that might also be another word you can use. R squared is going to be equal to the sums of squares regression divided by total. And then just using our simple properties that SSR plus SSE equals their sums of square total, you can easily derive this simple equation here. The interpretation of R squared is that it gives us the percentage of variability in Y, our response, that is explained by our regression or that's explained by our model. And that kind of makes sense because right here we have our SSR, which is telling us how much, if we remember from last video, SSR is going to equal, we're going to sum Y hat minus Y bar squared for each of the i's. So it's kind of telling us the difference between our model that we're predicting with and the overall mean. Some of the drawbacks of R squared are that it's never going to decrease as we increase or add more variables. It'll either stay the same or it'll increase a little bit. So more parameters, R squared's never going to decrease. There is something called adjusted R squared, which we will talk about, that does account for the increase of parameters. R squared is also going to come back into play when we start talking about model building in, I think, next week's lessons. But we're just trying to get an introduction to it and remember what it is from Stat 5615. R squared is going to always be between 0 and 1, where if we get an R squared of 0, we're going to indicate that there's no relationship. An R squared of 1 is going to indicate a perfect linear relationship. It basically, R squared is going to be it's a descriptive statistic for measuring the strength and dependency of the response on the regressor. It's not a test statistic for determining statistical significance. The one hard part, or I don't think it's really hard, but something that you should know is that there's no universal cutoff for a good R squared value. It really depends on your field. I know some fields getting an R squared of 0.23 or 0.3 is fantastic. Those are for the more the subjective types of fields, but then other fields were like kind of want you to be getting like a 0.8. So it depends on your field, and I would recommend looking at your lit review and your literature in your field to decide what would be a good cutoff for your model. To just explain how R squared works, here's a little picture where in this plot, we're going to have a small sums of squares regression and a small sums of squares error. So we can notice that our slope isn't too far off. If you could imagine maybe the overall mean, our Y bar being here. So our model isn't too far off from our Y bar. And so our sums of squares regression is small, so our R squared is going to be small. In this plot here, we're going to have a large sums of squares sums of squares regression. So if you could imagine it, maybe the overall mean would be here, so we can see a pretty big difference. And again, our sums of squared error is pretty small. Once we start to increase our sums of squares error, kind of that background noise, we'll start to notice that our R squared does get a lot smaller compared to when our SSE was bigger. And that just makes sense from a practical standpoint. If we have more error in our background noise in our data, it's going to be harder to estimate our parameters and whatnot. So let's go to the fish example and see how we interpret it and what our R squared is from that. So here's our fish example. We have our jump results and our R results. Again, they'll be outputted for you. Notice that there is the adjusted R squared here and here. That's foreshadowing. But how we would interpret this for our fish example is that about 91% of the variation in seasonal catch is explained by the model, which is pretty high. With that, we will conclude our lessons for this week. I would recommend going to go watch the Jump or R video to see how we got all the output throughout our lessons, and then get started on your homework, which is due Saturday. Great work today. If you have any questions, come to office hours or post messages on Slack.